Hi everyone, welcome back. This lecture today is going to be on analysis of covariance, called ANCOVA. So we've seen ANOVA already, analysis of variance. That's when you have one dependent variable that's continuous and multiple independent variables, well, one or more independent variables, each one of which is discrete. It has discrete levels, like placebo and drug, or drug 1 and drug 2 and drug 3, and so forth. In analysis of covariance, it's basically just like an ANOVA, except we add something to the model. We add another independent variable that's now continuous. So it's kind of like mixing linear regression with analysis of variance. In multiple regression, all of the independent variables were continuous. In ANOVA, all the independent variables are discrete. In ANCOVA, we have a mixture of discrete variables and continuous variables. Today we'll talk about one discrete variable and one continuous variable in the model, but you can have as many as you want. So these other variables, these continuous independent variables, are known as covariates, or sometimes people call them concomitant variables. And they're variables that have usually been collected for each participant in advance of the experimental manipulation. They might be, for example, pre-existing differences among subjects on some score, like age or income or blood pressure. And there's basically two ways that we use these covariates when doing ANCOVA. One way, we can use them before the experiment to experimentally control for pre-existing differences. So we could use the score on a covariate as a way to assign participants to groups, for example. If we wanted to match placebo and drug groups on age, for example, then age would be the covariate measure that we would use to match groups on. The second way we could use covariates, and that's what we're going to talk about today, is they can be used after the experiment is over to statistically adjust for pre-existing differences in the dependent variable and in the covariate. So we can allow then for variation in the concomitant variable, both within groups and between groups. And what we do during the analysis is we statistically account for the relationship between the covariate and the dependent variable. We statistically model that relationship, in fact, as a linear relationship, and we use that relationship to statistically adjust scores on the dependent variable to what they would have been if everyone was equal on the covariate. So we can allow for pre-existing differences in age, for example, and then statistically correct after the fact and kind of extrapolate. What would their scores have been if they had been equal on age? So let's look at a different concrete example. Let's say in September we assigned a different math textbook to two different grade 10 classrooms. And we want to see if different math books result in different test scores on the Christmas exam. So we can select 10 students at random from each class. Each student takes a 25-item math test. And we also happen to have, let's say, students' scores on an IQ test that were done before they learned about this math class. So the IQ scores allow us to ask the question, now, to the extent that we believe IQ is meaningful, which personally I don't, but this is just an example. So we could ask the question, is there a difference on the post-test, on the math test, after pre-existing differences in general intelligence are accounted for? So ANCOVA is a method to account for the relationship, if it exists, between a covariate and a dependent variable. It's a way to statistically adjust for differences on the concomitant variable by including it in the model as a predictor variable. So ANCOVA is just like regular ANOVA in terms of the model comparison approach. We're going to compare a restricted model to a full model. But now one of the variables in our model, i.e. the covariate, is a continuous variable. So here's the key question that is answered by ANCOVA. Would the groups have been different on the post measure, on the dependent variable, if they had been equivalent on the covariate? In other words, is the observed difference in the dependent variable due to our experimental manipulation, or is it simply due to the pre-existing differences on the covariate? So that question only really makes sense then if there's a relationship between the covariate and the dependent variable, right? If there isn't, then pre-existing differences in the covariate wouldn't be expected to have any effect on the dependent variable. But if there is a relationship between the covariate and the dependent variable, then if there are differences in the covariate, then we could reasonably suggest, well, if they're different on the covariate, and the covariate is related to the dependent variable, then maybe the only reason they're different on the dependent variable is because of the differences on the covariate, and not because of our experimental manipulation, the drug, for example. So the logic of an ANCOVA goes like this. We can include the covariate in the model, and that affects the analysis in two distinct ways. First, the within-group variability is going to be reduced. Remember, the within-group variability in our ANOVA model is a measure of the extent to which the data are different than the average within each group, right? It's those vertical distances between each data point and the group mean. By allowing that group mean to be not a horizontal line, but a line with a tilt, with a slope, we can reduce those vertical distances. And we can allow that line to be a sloped line because we're going to model the relationship between the covariate and the dependent variable. We'll see what this looks like in a few slides. So the bottom line is the within-group variability, the error term in our ANOVA, is going to be reduced. And it's going to be reduced by an amount that depends on the strength of the relationship between the dependent variable and the covariate. And it's typically a pretty substantial reduction in unexplained variance in our model. So we get a smaller error term, and we get greater statistical power to detect differences if they're there. The other thing is we get an increase in the estimate of the effect size. Again, because the denominator of that effect size measure, whichever one we use, the denominator is related to the unexplained variance. And if we can reduce that unexplained variance by explaining some of it using the covariate, we get an increase in the effect size. Now, just a note about the sort of idea of statistically correcting after the fact. It'll only equate groups statistically on the covariating variable, right? It's not a substitute for true random assignment to groups. Randomization, random assignment, random sampling over the long run guarantees that groups will be equated on all relevant dimensions, not just the covariate. When we do the statistical adjusting after the fact, it's only based on one variable, on the covariate. People or subjects in the experiment could be different from each other on all sorts of dimensions, not just the covariate. And of course, we can't statistically correct for all of them. So the only real way to do that properly is through random assignment. Okay, let's look at another fictitious example that's going to help us work through the logic of this some more, and we'll see some graphics that'll help us understand how this works. So we know from neuroscience, and you probably have seen this already, the hippocampus is a brain structure that's thought to be involved in memory and in spatial memory as well. So here's a scientific question. Is the volume of the hippocampus greater for taxi drivers than for people who aren't taxi drivers? And indeed, there was an fMRI study looking, or not an fMRI study, an MR study looking at the size of these brain structures in taxi drivers in London, England, who are known to have these incredible spatial memories for all of the strangely shaped streets and avenues in London, England, which are plentiful. So, is the volume of the hippocampus greater for taxi drivers than for people who aren't taxi drivers? So, let's say we do a study where we have two groups of people, either taxi drivers or people who aren't taxi drivers. We scan them with an MRI scanner. We estimate the volume of their hippocampus and we compare them. But let's say we also know that the hippocampus volume is also affected by age. Now, just note that I'm making this up for the purpose of this example. I don't know actually if the hippocampus volume is affected by age. I suspect it is, but this is just for the purpose of illustration. So if we know that the hippocampus volume is affected by age, and if we know that not everyone in our taxi driver and non-taxi driver groups are exactly the same age, they might be close, but they're not going to be exactly the same age, then we can include the age of each participant, which is a continuous variable, as a covariate in the analysis. And by doing that, we're essentially saying we can probably account for some of the variation in hippocampus volume from person to person because it's affected by age. So let's account for that in the model. So here would be our restricted model and our full model for ANCOVA. In the restricted model, each score on the dependent variable y, the ith score in the jth group, would be proposed to be equal to mu, some grand mean, plus beta times x, ij, where x is the covariate, x is age. So in the restricted model, hippocampus volume is determined by the average hippocampus volume of all humans plus or minus some slope on their age. And that beta weight determines how much hippocampus volume changes with each year of age. And that's it. That's all that determines hippocampus volume in the restricted model. That's the null hypothesis. The alternate hypothesis, the full model, says no. Hippocampus volume is determined not only by age, but also by alpha sub j, which is an effect of being a taxi driver or not being a taxi driver. Alpha sub j codes for the group that the participant is in, group 1 or group 2, taxi driver versus not taxi driver. And so that parameter alpha determines how hippocampus volume changes whether you're a taxi driver or not. And in the full model, which is the alternate hypothesis, the proposal is alpha j is not 0, right? When alpha j is 0, then we have the restricted model. We have the null hypothesis, which is the only thing that affects hippocampus volume is age. In the full model, we're saying it's age plus the effect of being a taxi driver or not. Okay, so Yij is the score on the dependent variable. Mu is the grand mean, the average hippocampus volume of all humans. X is the age of each participant, and beta is the parameter that we're estimating, the slope of the hippocampus volume as it depends on age. Alpha sub j is the treatment effect, taxi driver versus not taxi driver. That's the discrete variable. And epsilon, ij, is noise or random variation or unexplained variability. That's essentially the error term in our model. So we've got two competing models. They both include the covariate, importantly. ANCOVA is not a test of whether the covariate should be there or not. In ANCOVA, the covariate is there in both models. What's missing from the restricted model is the discrete variable, is the factor. So ANCOVA is asking the question, is there an effect of the factor in the context of a model that includes the effect of the covariate? So the covariate is always there. The missing one is the factor, and that's the thing that we're interested in testing. Once we account for variability due to the covariate, Once that's in the model, do we need the factor or not? Okay, what's the cost of doing all this, right? We've talked so far in the course, especially in multiple regression, about the idea that each time we have to estimate a new parameter, we have to pay for it with a degree of freedom. So what's the cost of including one covariate in the model? It's not that bad, right? All we're estimating is beta. We're estimating one additional parameter. So we only have to pay using 1 degree of freedom. 1 degree of freedom moves out of the error term, out of the denominator of the F ratio, and up into the numerator. And so it's not that severe of a cost, in fact. How is that beta parameter estimated? It's done using a least squares criterion, just like linear regression. It's the same idea as linear regression. We're regressing x onto y. So age would be on the horizontal axis, and hippocampus volume would be on the vertical axis. So here's a graphical depiction of the restricted model in ANOVA on the left and the restricted model in ANCOVA on the right. So on the left, let's say x is age. Forget the actual numbers. Let's just say x is age and y is hippocampus volume. In traditional ANOVA, we wouldn't include the effect of age on hippocampus volume. Our restricted model would only say that y sub ij, so hippocampus volume for all participants in all groups, is only due to mu, the grand mean, plus random variation. And so the vertical distance between each data point and the red line on the left would represent the error term, the denominator of our F ratio. On the right is the restricted model in ANCOVA, which says, no, hippocampus volume is determined not only by a grand mean, mu, but also is affected by age. And since we have measures of age on the horizontal axis, x, for each participant, we can model the relationship between age and hippocampus volume using that red line, which now has a slope. Right on the left, it's kind of like we still have beta times x, but beta is 0. So there is no slope to the line. On the right, we allow the line to have a slope. And so the vertical distance between each data point and the sloped line on the right are much smaller than the vertical distances on the left. And so we get a much smaller error term in the restricted model. And of course, we have to pay using degrees of freedom, but we only have to pay with 1 degree of freedom because we're only estimating one thing, one parameter, beta. So that's the restricted model in ANCOVA as it compares to ANOVA. So you can see immediately how it reduces the error term because those vertical distances are smaller. And this is before we even consider the full model with the factor. Here's what the two full models look like. So in ANOVA on the left, we've already seen in the last couple of weeks, the full model says hippocampus volume y is determined by a grand mean plus the effect of group membership, alpha sub j, right? So we have two different parameters, one for taxi drivers, one for non-taxi drivers. And now the vertical distances between each data point and the group mean is the error term. And if I just flip the slide back, the error terms are bigger in the restricted model for ANOVA than in the full model for ANOVA, because now each group gets its own mean, right? On the right is the full model for ANCOVA. So just like for the restricted model, what the covariate allows us to do is tilt those horizontal lines up, because now we're including the relationship between age, which is the x variable plotted on the bottom, and hippocampus volume, which is y. And so now the lines have a tilt. We still have two lines because now each line has its own intercept. The lines have their own, the lines have the same slope, right? Because there's only one beta. There isn't beta sub j. It's just beta. So both groups get the same slope, but because alpha has a subscript j, that alpha sub j plus mu, that acts as the intercept of those lines. So each group gets its own intercept. I mean, in the model on the left, in the ANOVA model, you can still consider those as two different intercepts, right? They just have no slope. Now in ANCOVA, they have an intercept and a slope. Now, we'll see later in the slideshow that if you want to estimate different slopes for each group, you can do that in ANCOVA, but you need to make sure that that's a rational thing to do. But the default ANCOVA model is all groups have the same slope. So alpha sub j in plane ANOVA, alpha sub j in ANCOVA, they're both representing intercepts. And in ANCOVA, that beta variable represents the slope of the line. And it's the same beta for all groups. So for ANCOVA now, we have a restricted model on the left that includes just the covariate, x, and allows the line to have a slope. So there's one intercept for all groups, one line for all groups. And on the right, we have a full model that says, no, let's have a line for each group. Each group could have its own intercept, but they both still have the same slope. And so the question in ANCOVA now, remember, the question is not, should we have a covariate? In ANCOVA, we go in assuming that the covariate should be there. The question in ANCOVA is, now that the covariate's in there, do we need one intercept for all groups, or does each group need its own intercept? In plane ANOVA, the question was, do we need one mean for all groups, or does each group get its own mean? Now the question isn't about the mean. Now the question is about the intercept. Do we get one intercept across all groups, or does each group get its own line with its own intercept? So, by including the covariate, you can account for more variability in the data. Those error terms get smaller when you allow those lines to have a slope. We can also, as we'll see shortly, we can also statistically adjust for pre-existing differences if they're there between groups in the covariate, and sort of project what would the dependent variable have been if groups had been equal on the covariate. Now, if the covariate's not linearly correlated, not linearly related to the dependent variable, then there's not going to be any beneficial effect of using ANCOVA, right? I mean, if you plot x versus y, and there isn't, the data doesn't appear to have any slope at all, then you can still include the covariate, but that beta parameter, the slope, is going to be estimated near zero. And so you're not going to do anything beneficial. You're not really going to reduce the error term, and you're going to have to pay for that using 1 degree of freedom. So it's not a good deal. The covariate being in the model is only a good deal if it is linearly related to the dependent variable. But, of course, the covariate has to be independent from the experimental treatment. It can be related to the dependent variable in a correlation kind of a way, but it has to be independent from the experimental treatment, and we'll see that later. So let's talk about this statistical adjustment that I've been mentioning a couple of times now. Once you account for that relationship between a covariate and the dependent variable, you can generate adjusted means for each group. That allows you to answer the question, what would the means of each group have been if the scores on the covariate had been equal across groups? So if the groups differ on the covariate, you can statistically adjust the dependent variable to kind of extrapolate what would things have looked like if participants had been equal on the covariate. So let's look at some graphical examples to see how this might work. Let's say in our hippocampus experiment, we didn't do a good job of equating the two groups on age. So let's say we have our taxi drivers in blue and our control non-taxi drivers in pink. And you can see that the hippocampus volume of the taxi drivers is lower on average than the hippocampus volume of the controls. On that vertical axis, taxi drivers are lower, controls are higher. Now, you can also see, however, that the age of the taxi drivers happens to be lower, the average age happens to be lower than the average age of controls. Ideally, we would have equated the two groups on age, but let's say we didn't and we have taxi drivers that happen to be younger than controls. Let's also propose, and this is the part that I'm just making up, that hippocampus volume increases with age. You know what? It probably decreases, if anything. But for the sake of argument, let's assume that hippocampus volume increases with age. So now the question is the greater hippocampus volume in controls due to the fact that they're not taxi drivers? Or is it just because they're older and we know that hippocampus volume increases with age? Right? So we've got a pre-existing difference on the covariate. We have an intuition that the covariate's related to the dependent variable. And we have a difference on the dependent variable. And so now we want to kind of untangle that difference in the dependent variable. Is it due to the manipulation, taxi driver versus control, or is it due to the covariate difference in age? So hippocampus volume of group 1, taxi drivers, is less than group 2, controls. Oops, but our controls tended to have higher age. So can we statistically control for these pre-existing age differences and adjust scores on the dependent variable? So what would hippocampus volume have been if the age of both groups had been equal? They're not, but what if they were? So we have to come up with some proposed age to project both groups onto. And the natural thing to do is just take the grand mean of age across the whole experiment. So that black vertical line is the average age across the whole experiment. So now we can ask the question, given that there's a relationship between hippocampus volume and age, what would the hippocampus volume of the controls had been? What would it have been if the control had been the average age on the black line, not on the pink line? And what would the hippocampus volume of taxi drivers have been if their average age was the black line, not the blue line? So XM is the average age across the whole experiment. So if we draw a line that characterizes the relationship between hippocampus volume and age, we can kind of draw an arrow up to that black line. That big blue dot now, that's what the average hippocampus volume of taxi drivers would be if their average age was XM. That's the adjusted mean of the taxi drivers. And similarly, that big pink blob now is the average hippocampus volume of the controls if their mean age had been XM. Oops, sorry, I flipped through that too quickly. Let's bring that back. So we use this linear relationship to extrapolate up or down and say, what would the hippocampus volume of taxi drivers have been if they were XM and not X1 age? And similarly, what would the hippocampus volume of controls have been if they were XM average age, not X2 average age? So if we equate the two groups on age, hypothetically, taking advantage of this known relationship, this modeled relationship between hippocampus volume and age, we can extrapolate up or down and find new adjusted means on the dependent variable, hippocampus volume, for the two groups. And in this case, it would actually completely flip the effect, right? When we equate the two groups on age, now taxi drivers, according to our model, have a greater hippocampus volume than controls. Whereas before, the raw means, the raw averages, taxi drivers had a lower hippocampus volume than controls. So by statistically adjusting for the effect of age on, or the relationship between age and hippocampus volume, we've completely flipped the order of the effect here, which can happen. And those are called adjusted means. So there's a variety of scenarios you can have. You can have a scenario like this, where the estimate of the treatment effect decreases by adjusting for pre-existing differences. So here's a case where y1 is much less than y2, but if we equate them on the covariate x, the difference between y1 and y2 on the vertical axis, that difference decreases, they get closer together. You could have a situation where the estimate of the effect increases when you adjust for pre-existing differences. Here's another example where y2 is y2 is bigger than y1 on the vertical axis. That's the unadjusted difference in means. But when we equate them on the covariate x, the treatment effect, the difference between y2 and y1, gets bigger. Here's a case like in our hippocampus example, where the estimate of the treatment effect is reversed by adjusting for pre-existing differences in x. y2 is less than y1 in the raw means, but when you equate them on x, y2 is greater than y1. So we saw in our previous example where you can have the adjusted means reversed compared to the raw means. In this kind of situation where there's more of an overlap on the covariate, you can have a situation where the difference between y1 and y2 is decreased or even goes away when they're equated on the covariate. You can have a situation where the difference is just reduced a little bit, still there but reduced. So the point of showing you all those hypothetical examples is to point out that when you perform this statistical extrapolation, this statistical adjustment, and you compute adjusted means, depending on how those groups are sitting on the covariate, you can have an increase in the effect, a decrease in the effect, a reversal of the effect, or an abolishment of the effect altogether, depending on the configuration of all the data. So that's adjusted means, and that is one important way that ANCOVA is used to statistically adjust for differences on a covariate. But like we talked about before, ANCOVA can help you out even if there are no pre-existing differences on the covariate. So here's a situation where we have the dependent variable y and the covariate x, and we have two groups, y1 and y2, and y2 is greater than y1 on average on the dependent variable. So we've got relatively large error terms. Remember, the error terms are the difference, the vertical difference between each data point and the group mean. The two groups are basically completely overlapping on the covariate, right? There's no difference in the average value along x. The two are overlapping. But if we include the covariate in the model, we allow those horizontal lines to have a slope. And so now the vertical distance between each data point and the sloped lines is much smaller. And so even if there are no pre-existing differences on the covariate, including the covariate could help us account for some of the variability in the data. It helps us model what's happening in the data. And the effect of that is it reduces the error term in our F ratio, and we get a more powerful statistical test. Remember, smaller error is the unaccounted for variability in the data. Smaller error means a larger F and more statistical power to detect effects. We do have to pay for it because we have to estimate that slope, but it's only one parameter across the whole experiment, and so it's not a very expensive parameter in terms of degrees of freedom, whereas it could explain a lot of the variability, especially if there's a strong relationship between the covariate and the dependent variable. Okay, so by including the covariate in the model, we bring about a substantial reduction in the unaccounted for variability in the error term. And we do that because we are modeling. We're modeling using a linear model, using a straight line. We're modeling the relationship between the dependent variable and the covariate. So we get greater power, statistical power, for detecting treatment effects of the factor. And the other thing we can do, if there are pre-existing differences on the covariate, is we can compute adjusted means on the dependent variable that allow us to ask the question, well, oops, the groups were different on the covariate, and there's a relationship between the covariate and the dependent variable. So, oopsie, these differences on the dependent variable, how much are they different because of the covariate being different, and how much are they different because of the treatment effect, the groups? Let's extrapolate. What would those scores on the dependent variable have been if everyone, all groups, were the same on the covariate? And we use that linear model of the covariate to project up or down and extrapolate, essentially, an adjusted mean on the dependent variable. So there are some assumptions of ANCOVA, of course. In the usual way, there's a normal distribution assumption. The little extra bit in ANCOVA above ANOVA for the normality assumption is the assumption is the scores are normally distributed at all values of the covariate. So remember, there's a relationship between the covariate x and y, and the assumption is at all levels of the covariate. So at all ages, for example, hippocampus volume is normally distributed. That has to be true. The other assumption is called homogeneity of regression, and this is the assumption that we talked about already, which is that that there's only one slope. There's only one beta coefficient. So the homogeneity means sameness, and of regression essentially means the sameness of the slope across all groups. So the assumption is the slope of the relationship between the covariate and the dependent variable is the same across all groups. Therefore, only one beta coefficient. You can test this, of course. I mean, it might not be true that homogeneity of regression is valid. There could be heterogeneity of regression, which would mean each group has a different slope between the covariate and the dependent variable. And in that case, you would want to include a different beta parameter for each group. You would want beta to have a sub j. So now you'd have to estimate more parameters, a slope for each group, and you'd have to pay for each of those slopes with a degree of freedom, which you could do. It's easy to put that in the model. But I think what you really would have to consider under this situation is what does it mean conceptually for there to be different relationship between the covariate and the dependent variable in the different groups? What would that mean? Especially if they overlap on the covariate, right? So in that overlapping region of X, participants have the same score on the covariate, but there's a very different relationship between the covariate and the dependent variable. That would raise questions in my mind, right? That would raise the possibility that something about group membership, or the experimental treatment alters the relationship between the covariate and the dependent measure, which might point to a lack of independence of the treatment and the covariate. And the reason that's a problem is because, although we can statistically adjust for differences in the covariate on the dependent measure, this doesn't experimentally control for potential interactions between the covariate and the treatment effect. It's a mathematical operation where we draw a straight line and we just march up or down that line and we say, well, it would have been this, right? If that person had been 27 years old instead of 48, their hippocampus would have been this big. Now, is that actually true? Well, you don't know because that person wasn't 27. They were, what did I say, 40 something. So the validity of that operation of computing adjusted means rests on this assumption that the treatment is independent from the covariate. Another example, what if the experimental treatment, like if it was a drug, actually has different effects on young people versus old people, right? We can't really tell unless we actually do that experiment. Statistically adjusting for the means on the covariate won't actually solve that problem. The only way to truly deal with it would be to equate the groups on age in the first place. Okay, that was relatively quick that we went through those slides. I encourage you to go back and rewind and pause and think about anything that was a little confusing. And in addition, read the course notes. So where are they? Here they are. ANCOVA. I didn't post a chapter reading from a textbook for ANCOVA, not really. Instead, I posted my own notes, which goes through the main concepts. And I think that's probably going to be better than pointing you to a more advanced textbook on ANCOVA. This is going to give you a summary of the main concepts. I did put a link to a chapter of a textbook by Maxwell and Delaney. I'm not allowed to put it on the web page because that's public. So instead, it is located in the Resources tab in OWL on the website for the course. So if you go down to Resources, it is down here, MD ANCOVA. And it's chapter 9 of this book, and it goes through the main concepts of ANCOVA. It's a little more of a sophisticated presentation. It's designed for a graduate course in statistics, but if you read it with an eye towards just absorbing the top-level concepts, then that is completely suitable. Read my notes and then have a skim through chapter 9 and see if there's anything that helps you understand it just by being perhaps worded in a different way. And if you're interested in more details, then that chapter is a good place to go for more in-depth material on ANCOVA. Okay, so that's ANCOVA. Let me go back to the models because this really encapsulates what it is. It's a restricted model that only contains the covariate and not the factor, versus a full model that includes the factor and the covariate. So I'll say it again, importantly, ANCOVA is not a test of whether the covariate should be there or not. The covariate's there in both models. The ANCOVA is, just like ANOVA, it's a test of the factor, drug, for example, or group. It's a test of the factor in the context of a covariate being present in the model, in both the full model and the restricted model. Now, you can think about the question of should a covariate be in the model at all? And think about what should be true for that to be the case. When would it not help you to have a covariate in the model? Well, we kind of talked about it already. If there was not a linear relationship between the covariate and the dependent variable, right? If this was not clearly linear, if they were not clearly linearly related, if instead these were just clouds with a slope of 0, then by putting that covariate in the model, these lines would still be horizontal. They wouldn't have a slope. And you would have had to have paid for that 0 parameter. The slope parameter would be 0. You would have had to pay for that useless 0 with 1 degree of freedom. So you'd only hurt yourself. So including a covariate in the model is only a good thing to do if you know that there's a linear relationship between x and y, if that beta parameter is likely to be non-zero. And so what assumption test or procedure could you do to ask yourself, I've got all these measures of my participants like age and socioeconomic status, income, and what else? Height, blood pressure. They have a memory score. I wonder if I should include one of those in the model to help. What could you do? Well, you could simply do scatter plots of your um, pre-experiment measures, your covariates, against the dependent measure, and just visually have a look and see if there appears to be a linear relationship. You could compute correlation coefficients. You could do a linear model, right? You could do a linear regression of each covariate against the dependent measure and estimate that slope, beta, and look at the significance test for that beta slope. If it's reliably different than zero, then maybe you want to include that in the model because there is a non-zero relationship. This beta parameter would be zero, and it will help you. So um, that's the reason why only a linearly related covariate is going to help you in an ANCOVA. Will it hurt you if you include variables that don't have a relationship? It will end up hurting you because, as I said, you're going to pay for a degree of freedom, but you're not going to get anything out of that. It's kind of like in multiple regression, just throwing in a whole bunch of variables that don't really account for variability. You have to pay for all of them with a degree of freedom, and that's going to increase your error term, which is going to give you less statistical power. Alrighty, I think that's all that I wanted to say with the